Since we are talking about chemical reactions, we need to know a way to compare the amounts of our chemicals. We usually use the mole as the SI unit, or as the way to quantify the amount of our chemicals in a chemical reaction. And the mole relates to Avogadro's number. We're going to talk about that as our learning objective. What is a mole? The mole is not the animal that lives underground. In this case, we're talking chemistry, not ecology or zoology. In chemistry, the mole is a quantity that contains 6.02 times 10 to the power 23 number of items. And these items can be particles. The particles can be ions, number of ions, 6.02 times 10 to the power number 23. The Avogadro's number relates to number of ions, number of molecules, okay, number of atoms, or formula units if you are dealing with a compound. So the Avogadro's number is really the 1 mole of count of particles, of ions, molecules, atoms, or formula units. So let's dig in. 1 mole of a carbon sample, 1 mole of a carbon sample will contain the Avogadro's number of atoms, because the carbon itself is an atom of the element carbon. So that's that. Also, for water, 1 mole of water, remember that water is a molecule, contains the same Avogadro's number, but at this time of water molecules, not atoms, but molecules, because H2O itself is a molecule, it's not an atom, it's not an ion, it's a molecule. And then 1 mole of vitamin C, 1 mole of vitamin C, which in that case that should be technically a compound. If you want to call it a molecule, is fine. 1 mole of vitamin C will contain the Avogadro's number of vitamin C molecules. To emphasize, the number 6.022 times 10 to the power 23 is what we call the Avogadro's number. And like I said, this number value can represent 1 mole of ions, 1 mole of atoms, 1 mole of molecules, or what we call formula units in terms of relating to number of particles of compounds. And that usually is the definition of the mole. You don't want to compare your chemicals in terms of grams, because they have different formula weights. But if we can use the mole, it's easier to relate and quantify the amount of chemicals that you're dealing with. The mole and Avogadro's number gives us a conversion factor that will help us to solve for the mole using this conversion factor given number of atoms, or solve for number of atoms given a mole or moles of a given substance. Or you solve for the mole equivalent of number of molecules given a given number of molecules, or solve for number of molecules given a given amount of moles of that molecule. So it's very important for us to know these 4 relationships, 1, 2, 3, 4, because you're going to use them a lot from now onwards. Let's see an example. Let's do problem 5.9. Question: how many molecules? You can read that. How many molecules? The moment you read that, that's a buzzer, that's a hint for Avogadro's number 6.022 times 10 to the power 23 number of molecules should be equal to 1 mole. That's a huge hint. We continue to read. How many molecules are contained in 5 moles of carbon dioxide? This is a molecule, it's a gas. So I'm given moles of CO2. I need number of molecules, which is why I said hint, 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 Avogadro's number relationship. And we're going to use version 4 of the mole relationship to Avogadro's number, because we are dealing with molecules and we are asked to find how many molecules. So this is a conversion factor we'll need. So what will I do in this case? I'm going from 5 moles and I'll need the number of molecules, which is why I'm going to relate the number of molecules to 1 mole, and the number of molecules relationship to 1 mole is the Avogadro's number. Okay, that's what defines the mole. 1 mole is equivalent to the Avogadro's number of particles, and those particles in this question, they are molecules. You set it up this way so that the moles of CO2 and this mole will cancel out. So all we need to do is to multiply the 5 by the Avogadro's number, and the answer that we should get should be 3.0 times 10 to the power 24 molecules. I've already rounded it to 2 significant figures that I have here. Okay, so that's how you solve this. Okay, so the conversion factor that we used was this, as shown in the slide. Why? Because we need the number of molecules. We don't need to end up with the moles. So this is not correct. Usually where you're going dictates what should be the numerator. So we'll have to write this the other way around, which is this conversion factor. And then all we needed to do was to plug in our given moles and plug in our conversion factor. And then keep in mind that units also can always cancel out, so that you keep the needed unit or SI unit for your answer. You get 30. You can report that to correct scientific notation, which is 3.0 times 10 to the power 24 molecules of CO2. What this is telling me is 3 times 10 to the power 24 molecules of CO2 is actually equal to or represented by 5.0 moles of CO2, because that's what the question was asking me. The question asked me how many molecules are contained in 5 moles of CO2. Let us do some examples of the relationship between the mole and number of particles, which is Avogadro's number. Question number 1 is how many atoms are present in 12 moles of sodium? So we are given moles of sodium. We need number of atoms. The number of atoms are needed. So which formula should I use for question 1? For question 1, I'm going to go with version 2 of the conversion factor, because it relates the number of atoms where I'm going to the mole. So I will set up my 12.0 moles here and multiply it by the conversion factor, which is 6.022 times 10 to the power 23 atoms. We need those atoms, so that's the numerator. Divide by 1 mole. Doing so, I'm going to get cancellation of moles and moles, which is what I want. And then all I need to do is to multiply 12 times 6.022 exponent 23. I hope you know how to use your calculator. The answer here is 7.2264 times 10 to the power 24. I see that the value given here is 3 significant figures, including the 0 after the decimal. And this is where it should be. So I see I have a 6, so I'm going to round up the 2 to the 3. So 7.23 times 10 to the power 24 atoms of sodium are equivalent to 12 moles of sodium. So that's it. Then the next one, how many moles are contained in this much number of atoms of calcium? It's 5.0 times 10 to the power 11 atoms of calcium. So this time I'm going to find the number of moles related to the number of atoms. So I'll have to use this conversion factor right here. Okay, so I'm going from the number of atoms to moles. So I'll need my mole as the numerator and my Avogadro's number as the denominator. Why do we need it set up this way? So that the atoms will cancel. Our answer will read something moles of calcium, which is what we want. So all that is left is for me to do the math. 5 exponent 11 divided by 6.022 exponent 23, the Avogadro's number. And if I've done it correctly, it should be 8.029 times 10 to the power negative 13. Okay, and that is going to be reported to two significant figures, which is here. So it's 8.3 times 10 to the power negative 13. Negative 13 moles of calcium are contained in that many number of atoms, 5 times 10 to the power 11 atoms. Question 3. How many molecules of water are present in 1.5 times 10 to the power 47 moles of a water sample? Which formula do we need? So we need version 4 of the formula because you're going to molecules from number of moles. And this is what I would set up to solve the problem. So we have 1.5 times 10 to the power 47 moles of water, but the conversion factor that will help us to go to number of molecules of water will be the Avogadro's number 6.022 times 10 to the power 23 molecules of water will be equivalent to 1 mole of the same water. Setting it up this way will help us to cancel moles of water in the denominator. Our answer would somehow read molecules of water because we did not cancel out the molecules unit in our calculations. All that is left is to punch in the numbers, and once I punch in the numbers, what I'm getting here is 9.033. Let me write that full first. So I'm getting 9.033 times 10 to the power 70 molecules of water, or water molecules. But I see our question is containing two significant figures in the value that we are given. So that's my two sig figs. 3 is less than 5. My final answer should be 9.0 times 10 to the power 70 number of water molecules. Now let us answer question 4. Question 4 is asking how many moles of oxygen gas are in 4.0 times 10 to the power 23 molecules times 10 to the power 23 molecules. So I'm going from molecules of oxygens to moles. So I think what I need is this version of my formula. That's what I'm going to use because I'm going to the moles. I'm given the number of molecules. So I'll put 4.0 times 10 to the power 23 molecules of oxygen, or oxygen molecules, and multiply that by the conversion factor of choice. I'm going to add the mole of oxygen relating it to the Avogadro's number relationship, which gives me the Avogadro number of molecules of oxygen, my answer will definitely read moles of oxygen. Why? Because the molecules and the molecules will cancel. This unit will stay. So now let me punch in the numbers and see what I get. So the answer I'm getting is 0.66423, maybe 1, 2. Now we need to report these to two significant figures, which will be this number right here, and that's gonna be 0.66, because the 4 is less than 5. I don't need to round this 6 up or down, I just keep it. So 0.6 is 66 moles of oxygen, but yet again I can report it to scientific notation as 6.6 times 10 to the power negative 1 moles of oxygen, being equivalent to, so that much moles of oxygen is equivalent to this number of particles of the oxygen molecules. All right, so our answer is this right here.